Hello everyone, I'm Krijn Doekemeijer from the University Amsterdam. Today I'm going to give a short presentation about the performance characterization of NVMe flash devices with the zoned namespace interface, which is represented at IEEE cluster as well. Today I hope to convince everyone that doesn't know what ZNS is, that ZNS is awesome and you should know about it. The people that do know what ZNS is, I hope to explain to you why its performance is so different and why we need this performance and how to use it. But before we get to the nitty-gritty details of performance characterization, I would like to give some background on why we should care. What is ZNS, what trouble does it, what problems does it fix, and why do we need it? And the amount of data in the world is ever increasing. In fact, it's expected that by the year 2030, we can generate over a yottabyte of data every single year. And puts in perspective, my laptop here only has a terabyte, meaning we need 10 to the power of 6 or even more laptops every single year to hold all this data. And a large part of this data will be used by big data and HPC communities. And in the past, they typically tended to use slower storage devices such as hard disks, indicated by this nil. In the past decade, as the demands kept increasing, we largely moved to a faster storage device known as flash disks. This could have been done painlessly as clever firmware developers allowed us to use this very same interface that we used in the past, allowed us to still do the simple read, writes, anyways. In other words, we call this the block interface. Both HDD and flash sticks support the block interface. Supporting this block interface does not come with these issues, as you will see today. They will explain that one block interface does not perform for flash, which is the main problem that ZNS tries to address. There's now the new ZNS interface itself, which promises better performance, more stable performance, and should be a match for flash. But ZNS performance characteristics until now were not really known. And this is where we wanted to make a change. We tried to invert ZNS performance characteristics to see if it actually is a good match for flash and allows us to get to our needs that we need in HPC. Give a short recap. What exactly is this block interface talking about? What is this problem? What even is it? Block interface is very simple. It allows random reads and writes anywhere. So if you can imagine the entire stock device as one big array, increment addresses from 0 to 5. On the block interface, it means that we can write to both empty pages, written pages. We can do it anywhere. We can write to 0, 1, 3, 5. It really doesn't matter. It's the same for us. With flash internally, it does not work at all. Flash only allows for sequential reads. In other words, look at the picture here. And you want to write. You can only ever write to address 4, which is known as to write it. All pages before is already written and cannot be overwritten, and all pages beyond the 4 are beyond it. And that would break the sequential write-only constraint. Reads, on the other hand, can be done anywhere, or leading to complex asymmetric interface. Some of you might already be thinking, if we cannot overwrite data, does that mean that the device is basically useless? How are we going to reuse all of the storage? To explain this, I'd like to give a bit more into the internals of flash. Internally, these are many subregions known as blocks, each block being sequential write only. If you want to reuse the data within a block, there's a unique operation, flash specific, known as a reset. A reset deletes all data within a block, claims a resources, and allows us to write from the beginning. Now, sometimes you don't want to delete all data. In other words, how are we going to only remove part of the data that keeps some part of it alive? This is typically done to something known as a data migration. The data migrations is visualized here. Say we have a block 1. There's 3 valid pages and 1 invalid page somewhere in the middle. During migration, we first copy live data that we want to keep to a new block, visualized here as block 2, and then we set to all data. Essentially, we do work twice. Internally, what Flash needs to do is if we want to support the random block interface, and we have completely different. These things happen on the background without our control, completely black box, concurrently with client operations. And this is the pulse, like significant pulse, as we will showcase next. What we are looking at is what happens if we keyword into this. What about those data migrations? Do they actually hamper our client? Here in the pit, and we consistently keep writing to the same SD and SD. We see something. First, it seems performance is a bit stable, it goes up and down. So I'm 500 megabytes, gigabytes. It's all right, not too good, not too bad. And suddenly, it crashes like insane. It goes from more than a gigabyte to a couple of megabytes per second, a 120 factor. This is, of course, completely unacceptable. CMP data. Remember, we don't change our book. We don't do it more intensely. We don't do anything differently on the host. This is all because of firmware within this. This is because the block interface on the background does data migrations beyond our control. This is not even stable. In fact, cross background, you might think, well, problem solved, it's only temporary. No, it goes back and down and down. We have no idea how, we have no control over. As you see, big data, any applications. For industry and academia alike, we're looking for new interfaces. Recently, the most promising candidate yet has shown the ZNS, the zoned namespace interface. ZNS is very similar to the interface, as we will soon see. Exposing everything that we know about block, or about Flash, I mean, to us directly. Internally, it's divided into contiguous append-only regions known as zones, similar to the concept of blocks. On each zone, there are 3 support operations. Sequential write, very similar to what we have for blocks. And then read, very similar to what we have in blocks. Flash and reset, again, very similar to blocks. What we see is we have the exact same things as Flash during supports, but now exposed to us. So now we can do that modification ourselves. We don't have on the background. We don't get those drops anymore. At least that's what we hope. Because now we ones who can do it. This is complexity, because this is all exposed to the user. An easy individual zone of states. In fact, this is the zone finished state diagram simplified for one ZNS zone. The zone can be empty, it can be open, it can be closed, it can be full. And each of these zones allowed operations differ completely. And we all need to take this into account. But this leads to our main problem. This is just complexity. But for this complexity, we do not have performance. We don't have performance of simple write, read, reset operations on ZNS. We don't know if it's actually stable. Does it actually even deliver performance guarantees that we want to have from our Flash storage? The ones we need for stable throughput, stable latency. We don't know. What are the zone operation costs? What are all these state diagrams? What are the transition costs? We simply don't know. There's a real problem here. What are the ZNS performance characteristics? We intended to find out. To do this, we made a characterization for ZNS. Just of a set of micro benchmarks and scalability tests. We test simple single operations like appends, writes, and reads. We tested all zone management operations to see if which one are expensive, which one are cheap, how they work together. Did a more interference tests. Those who are like experts here that watch this video about Flash storage know all about that writes and reads interfere. We wanted to see if it's the same thing here in ZNS. It's like, is this bubbled up? Is it exposed to the users? And we tested our framework on a real SSD generated generously donated to us percentage. The AutoStar DC ZN540. And we found 13 key observations. And from these key observations, we were able to make 5 recommendations. Of course, this might depend a bit on the SSD. We still know the things that we need to look for. We need to know which operations, how do they like behave internally, what are things to look out for. And today we will discuss the 4 biggest observations. Actually, they are big because they have such a big impact on application design. And they are such uniqueness. These are things that we did not think were actually possible. These are really the cool ones. By the way, an entire framework that is open source. You can test it out on your own ZNS frame, ZNS SD. You can also play around with it, see a bit how we benchmark ZNS. We urge you all to look at it. But without further ado, let's now get into our 4 observations. By the way, the structure that we use to explain our observations, first we give some background, then we explain what we want to see, well, not what we want to see, but what we are going to look at for results, and then we're going to give recommendations based on observation. So the first one relates to how you do writes on ZNS. I explained earlier, zones are sequential write. You can only ever write to the head of a zone. This is done one by one by one. Of course, it doesn't scale. Clever people have come up with a new operation known as an append. What an append does is, it's still sequential write, but then on the device. You issue a request to a zone, then alter the zone, and then the zone and the ZNS itself returns the address on completion. So now it's up to the device itself to ensure like sequential writes. But we can issue many to the same zone, allowing us to probably skip. But now we need to pick which operations do we want to use for our needs. And this is very interesting, because say we have a latency sensitive application, like a website, something that needs like load a lot of stuff, or like the really big cool HPC stuff. What operation do we then need to use? What do we need to use for low latency applications? What we found is that for LSD, we tested, we found that there's a big difference. And one really needs to consider what one to use in such scenarios. We found that sequential writes are significantly faster. 11.2 microseconds, while the other one is 14 microseconds. That are the conclusion that yes, these use currently writes for lower latency. Now one might think, well, what operation would we use if we actually need high throughput? I want to get a lot of data through to the SSDs. Just do it on our around. Whereas we also like to consider a different scale. We already know sequential writes to scale. They are like slow, one at a time. We know that some appends allow many to be issued to the same zone. But while one zone might be sequential write only, what if we use issues IO to multiple zones concurrent? There is no constraint there, which I think is very neat. It's already used in a couple of like real research work for CNS. Which operation of these 2 always on the right do you want to use for scaling or throughput? If you look at the resulting plot, we see on the x-axis the number of in-flight requests. It's the number of current request issues. For appends, this means the number of requests to one zone. For right, it means the number of concurrent zones. We find that both are easily able to satisfy the peak throughput. But for our SD, writes reach them at 2 and appends at 3. So I might naively think, well, let's just use writes again. Let's just not use your appends anywhere. And that is something that might not explain. Right? I know I have explained it. The number of concurrent zones that can be used by any application is limited by a limit known as the active zone in the open zone. Only a set number of zones can be used concurrently at any time by any application. This is shared among all applications. So if one application uses all of these zones, nothing is left for you. The scaling through concurrent zone actually hampers concurrent applications. In other words, therefore, we recommend to use appends to scale throughput. Interesting, right? So you need to use appends in one scenario and writes in the other. Next result is the one that I really want you to keep attention. If there's one result that I want you to remember from this presentation, it's this one. This is the one to keep. It is, does CNS lead to the same performance variability as the block interface did for flash systems? In other words, do we get the same wobbly line as we have here, all up and down. We have an interface that can actually read consistent write throughput all the time. The short answer is yes, absolutely yes. Responsibility, use ZNS. It's plotted here as the green line circling around the red circle. And you see that it keeps going consistently throughout the entire time from beginning to end. So finally we have an interface that can deliver response. Really cool. Now, here is the last result. And this is personally my favorite because it's something that I didn't like a bit will expect about the new reset operation. New reset operation comes in essentially two flavors on ZNS. The pure reset and the finish. The pure reset turns an open zone to an empty zone and removes all data with it, allowing the zone to be reused for new data. And it transitions the write back to the beginning. The finish does the entire opposite, which is very confusing at first, right? Because why would you ever want to completely fill the rest of the zone, like junk or methods? The short reason is something I've already said probably before, which is the, again, the active zone limit, reopen zone limit. For an application uses many zones concurrently, it might use up too much resource and then needs to essentially transition the zone to a different state so that it releases. This can be done with a finish as it transitions to a full. The point of bypass operations is that they are highly dependent on how much work is within the zone, because say I reset needs to delete the data in the zone. So does its performance depend on the occupancy? In other words, the zone is half full. Is it cheaper to reset than if the zone is completely full? And for a finish, if the entire zone is empty, is it more expensive than if the zone is half empty? We intend to find how to find it. Was, in my opinion, shocking. We found that the pure reset is very expensive. It's on the order of milliseconds. Put in perspective, writes take microseconds. So we now know that these are very expensive operations that need to be done. We also found that their performance depends a lot on the occupancy. You see that for an empty zone it takes a millisecond or two, but for a full zone it took 1 hour, 15 milliseconds, which is 15 factors higher. So any application that needs to do any scaling related to resets, be it the scaler, be it the file system, be it the database, whatever, needs to truly consider the occupancy when thinking about its cost. And the other operation, the finish, is even more expensive. Like, look at this. This is almost a second. The finish can take up to almost a second. And the reason for this is that the SD that we use has almost 2 kilobytes as a zone size. So the zones are really big. And when you finish the zone, it tries to fill it up with data, which it does with writes. Essentially, what we see is if the zone is almost empty and you finish it, internally it keeps writing. What we're seeing is the write bandwidth to write 2 gigabytes, which takes almost a second. Really interesting. And hence also its performance depends on occupancy. But the inverse of resets, the more is in the zone, the cheaper the finish becomes. But what we see from both operations is that both are really expensive on the order of milliseconds and they depend on occupancy. In other words, we should prevent issue alcohol. Give a short recap or conclusion of our results. Remember, we found that on ZNS, for low latency, you use sequential writes, high throughput, you want to use appends. ZNS finally delivers the stability that we want to have for so long. ZNS set operations should be avoided at all costs. They are extremely expensive. And we're able to get all of our previously unanswered questions. We know the right meeting set points. We know if it's stable. We know the zone. Many of those things are not discussed directly in the presentation, but can be found in the paper. Please look at the IEEE cluster. The link to the paper is in the description below. And there are a couple of things that I really want you to remember from the presentation. If you don't need to remember all of our debates and recommendations. I really want you to remember is that block interfaces do not lead to good performance. But ZNS finally delivered and get the high throughput stable performance. If you wanted to have an HPC, big data, generally any storage bounded application, any big. But ZNS has a unique performance model, and we need to be careful.